For this video, we are going to recall the axiom of choice. This is important as we are to prove again the previously presented measures such as the counting and direct measure. We're going to show that those are really measures. And take note that the second condition for a certain function to become measure, as defined also in the previous video, is the concept on the countable unions, and we will be having that later. So this axiom of choice will actually help us in proving such. So this is how it is stated. If a set of a sub I for I element of a certain interval is a non-empty family of pairwise disjoint non-empty sets A sub I. Before we proceed, this tells us that this is non-empty and that the elements of this are actually pairwise disjoint non-empty sets. That would mean in all of those elements, there are no common elements. That's why they are called pairwise disjoint non-empty sets. Then, there exists a certain set E, which is a subset of the countable unions, okay, such that the intersection of set E and any of those A sub I is a singleton set for each I element of your interval. Okay? What does this mean? Okay? As mentioned, the elements of said set are pairwise disjoint non-empty sets. And there would be a subset of the countable unions, let's say E, where the intersection of E to any of those A sub I elements of the set is a singleton. Singleton means there's only one element. Okay? That's another term for unit set. Let me illustrate in this manner. Say, for example, I have here A sub 1, A sub 2. They are illustrated in this manner, okay? Because they are actually, they should not be connected because they are pairwise disjoint, meaning there are no intersections between them, okay? Because if I'm going to make them tangent, that would mean they have one common element, and that's the point of tangency. Okay, so for example, all of these are elements of your set, and they are obviously pairwise disjoint because they are not intersecting sets. If we have here a certain E, okay, a certain set where the intersection, okay, of any of those A sub I is a singleton, that would mean if I am going to have something like this here, there's only one element connecting them. Okay, so this would mean that, say for example, A sub 1 is the intersection of the set A sub 1 and this E. We have also A sub 2 for this, A sub 3, and so on and so forth. Okay, so this is what we call about the axiom of choice, that certain set, okay, will only comprise of those intersections. Okay, and this set is a subset of the countable unions. Okay, so this is very important as we are going to again prove later on counting measure and direct measure probably, as we are going to look into the second condition for a function to become a measure function. This is the illustration of the axiom of choice and the existence of a certain set E being a subset of that countable union that comprise all the elements of those singleton sets or the intersections. Okay, so you can see the implication of this, as this will be used as a part of the proof, specifically on proving measures. We'll have that on separate videos. Thank you very much for watching.